Hey class, today we're going to look at circuit analysis. There are two ideas that will allow us to analyze any circuits, and these are Kirchhoff's rules along with Ohm's law. We talked about Ohm's law the other class. Ohm's law can be summarized as the resistance is the ratio of the voltage and current, or V equals IR. However, Kirchhoff's rules is the more important one to use before you can calculate the voltage, the resistance, and the current of a circuit. So let's go ahead and look at some examples. So I'm going to start off with a very simple circuit. Call this example 1. So let's look at a series circuit with 3 resistance. So I'm going to start off with, let's call this R1, R2, and R3. So here's our R1, R2, and R3. So let's just give them some numbers. So let's make them simple. And this time it's the same resistance for each one. So each one has a 10 ohm resistance. And let's call this EMF, give this a 9 volt resistance. So first thing, let's calculate the equivalent resistance or the total resistance of this circuit. So because this is a series circuit, the resistance, individual resistance, the sum of each one is the total resistance. So in this case will be 10 plus 10 plus 10. So you have 30 ohms of total resistance. So that is how we calculate the total resistance of a series circuit. You just add the individual resistors and you get the total resistance. Now let's take a look at the voltage. Now, because this is a series circuit, the sum of the individual voltages will be equal to the total voltage here. So we have an EMF of 9 volts. This, we don't know the individual voltages yet, but what we do know is that the circuit is just one simple loop. So here is where your current is going to flow. This is your negative end and this is the positive end. Recall before that we talked about the electron coming out of the negative terminal, but it is the conventional current flow that we look at when we're looking at the circuit. So it is the current flow that is allowing this circuit to work. So current is coming from the positive end of the terminal here. And as you see, the current coming from the positive end of the terminal will go through R3, then R2 and R1 before it returns back to the battery, the power source. There's only one path for that current to follow, going this way, this, and back to the terminal, to the battery here, because there is only one loop. The current will be the same. Oops. The current will be the same as the total current that is running through the circuit. So we can calculate the total current, which is using Ohm's law, V equals IR. The total current then is the total voltage divided by the total resistance. Since we know that we have 9 volts of total voltage, that's given, and we have just calculated the resistance of the entire circuit to be 30 ohms. So you have here 9 divided by 30, just double checking, is 0.3 amps of current. This is the total current that is running in the system. So the current that is coming out of the battery, which is 0.3 amperes or amps, is going to have to go through R3 and R2 and R1. So that means that the IT is the same as I1, that is the same as I2, it's the same as I3. And this is the rule when it comes to a series circuit. So since this is the total current, each one is going to be 0.3 amps each resistance. Each resistor is going to receive 0.3 amps of current. So now that we have calculated the total current and the individual current of each of the resistors, we can now calculate the voltage of each one. So we know that VT is the total volts here is 9 volts. We can calculate each one because now we know the individual current and the individual resistance are given from the beginning. So V equals I R. So the I is 0.3 amps each, and the resistance is 10 ohms each one. So this is going to receive 3.0 volts of current. Now, because they have the same resistance, it's going to receive the same voltage as well. So V1 plus V2 plus V3 is going to be equal to 9 volts, and each one is getting 3 volts. So 3 plus 3 plus 3 volts. So 3 volts each resistor. That is what they're going to be receiving. So in this example, we looked at Kirchhoff's rules in terms of the first rule, which is the loop rule. It tells you that the total current that is running through the circuit is going to be the same as the current that is running through each individual resistor in the circuit, because there is no other path to follow. There is only one path to follow. So each one of these resistance is going to receive the exact same current as what's coming out of the power source here, the battery or the EMF. If we look at another example here, let's take a look at example 2. This time we're going to have still series circuit, but this time we're going to be using different amount of resistance. So same 1, 2, 3. So this is our R1, R2, and R3. This time I'm going to give this 10 ohms, this is 20 ohms, and this is 30 ohms. I'm going to keep the total EMF of 9 volts. So recall again that the current is coming out of the positive end of the terminal, going through R3 to R2, R1, and then back. So this 9 volts, as it comes out of the EMF or the power source, some of this 9 volts will be used up by the resistor here. And as it goes through the loop, it will decrease so that at the end of this, it will return to the terminal with 0 volts. There is no more potential. So again, let me go back to my first example here. This 9 volts that is coming out of the EMF is going to drop off 3 volts here, as we calculated 3 volts each of the resistor here. 3 volt is going to be dropped off here. So you started with 9 volts. Okay, when it comes out of the resistor here, this is going to use up 3 volts. So there's 6 volts left here coming out of that resistor. So as it enters the second resistor, you still have the 6 volts coming out of the first one, and 3 volts is going to be used up by R2. So now you have 3 volts coming out of that resistor. Now it's going to enter this R1 with 3 volts. And so after the 3 volts has been used up by this resistor, you have no more volts left. So recall that the voltage essentially is the kick. It's the pressure or the pump that drives the electrons out of the power source. It is the flow of these electrons that create the charge, and it is the charge over time that creates the current, and this is what drives the voltage. So it is the voltage that drives the electrons, that drives the current. So they do depend on each other as well, the current and the voltage. Okay, so in our second example, we still have a series circuit, but this time we have different amount of resistance, and you're going to see what happens to the voltage and the current as we calculate them. So let's take a look at the total resistance. Again, this is a series. So in a series, we have sum of each individual resistance making up the total resistance. So you have 10 plus 20 plus 30 ohms, and you have 60 ohms total resistance for this circuit. Now let's take a look at I'm going to look at the current first. So the total current, again, this is a series. The total current is going to be the same as the individual currents in each of the resistors. So let's calculate the total current. So VT over RT from Ohm's law. The total voltage is 9 volts and the total resistance is 60 ohms. So our total current here is 0.15. So 0.15 amps is the total current. So that means that the I1 equals I2 equals I3 is also going to be 0.15 amps. Again, recall that in a series, what is the same is the current. So we have to look at, when we're analyzing the connections, what will they have in common? What would each resistance have in common with the other resistors? Well, in a series circuit, they will have the same current, but the voltage is going to be different. So now we can calculate the total voltage is IT over IT times RT. The total current is 0.15 amps and the resistance is 60 ohms. So, we know this is 9 volts. So I'm just going to check. It actually works out to be 9 volts, but we knew that. We knew that the total voltage is given. So what I'm actually calculating here is the individual voltages. So V1 is I1 R1. The current is 0.15 amps, and the resistance of the first one is 10 ohms. So this is going to give me 4.5. This is 0.15 times 10 is 1.5 volts. This is our V1. And our V2 is going to be I2 times R2, which is, again, it's 0.15 amps. And the R2 is 20 ohms. So the V2 is 3 volts. Now let's just finish calculating the voltages here. The V3 is I3 R3. Current is still 0.15 amps. The R3 is the highest of the 30 ohms, and this is going to be getting 4.5 volts for the V3. Now let's take a look at the comparison here. Let's compare R1, R2, and R3 in terms of the strength. R3 is 30 ohms, so it's greater than R2, and R1 is the one that is the lowest one. If you take a look at the current, there is no difference because it is in series. And when we look at the voltages, V1, V2, and V3, you notice that V3 is the greatest one. Why is that? Well, because if you look at the resistance of R3, you have the highest resistance of 30 ohms. So in order for the current to power up the third resistor, you're going to need more kick, higher voltage. So you have more voltage in R3 because it has the highest resistance. So in other words, R3 is fighting the hardest. It has the highest resistance, so it is fighting that flow of current the hardest. So it needs to be pushed the hardest. So I hope that makes sense. So we looked at again, in this case, this is a series, so it is a loop. There's only one path to follow. So if you were to turn on R1 and you don't want R2 and R3 off, you really don't have a choice. In a series circuit, it's either all on or all off. You have to turn, even if with a switch, if I put the switch anywhere in this loop, once you turn it off, every single one of these resistors will be turned off, or on if you turn it on, because there's only one path for the current to follow. Let's talk about a parallel circuit. So in my third example, looking at a parallel circuit. So we're gonna be looking at the same resistors that I used in example 1. They're all 10 ohms. I'm going to draw it this way. Again, in a parallel circuit, you have junctions. You have junctions right here. And as you can see, because you have these junctions, the current that is coming out of the positive terminal here, when it encounters this junction, it has a choice. It can either go straight this way or turn this way. So you have junctions. We can apply the Kirchhoff's junction rule when it comes to voltage. So let's just label our R1 here, R1, R2, and R3. In our example here, I'm going to make them all the same, just like in example 1. These resistors all have 10 ohms of resistance each. And for the total voltage or EMF, I'm going to give this circuit 9 volts of potential difference. Now, the first thing you want to ask yourself when you're looking at a circuit and analyzing it in terms of voltage, current, and resistance is, what do they have that is the same in a parallel circuit? Because you have the same resistance here, okay? but you have junctions. It really doesn't affect the voltage that is going to go to R1 versus the voltage that is going to go to R2. So there is no weakening of the pressure or the kick that is coming out of the EMF here, because the kick that is going through R1 is not going to affect the kick or the pressure that is going to go through R2 and again going through R3, because they have junctions or different paths to follow. So here's one path, one here, and the other path is go straight into R2 and so on. So remember that in order to power up this resistance here, the current I actually has to go back to the terminal that way in that path. So if I turn off R2 or R3, R1 can still work, and vice versa. So if something goes wrong with R1, for example, or let's say the light bulb goes off, or the wire is broken, or if there's a switch that I put right here, R2 and R3 can still operate because it has more than one path to follow. The current is going to take different paths. So what is the same in a parallel circuit? They will have the same voltage because of the junction, okay? So because they have different paths to follow, the V1 right here, V1 is going to receive 9 volts because that is not going to be affected by the pressure that is going to get into R2 and R3 and so on. So V2 is also going to take this path that is unaffected by R1 and R3. This is also going to be 9 volts, and that is the same for R3. V3 is also 9 volts. So now that we know, we've analyzed that what is the same in a parallel circuit is the voltage, we can then conclude that each of these voltages of each of the resistor is going to take the exact same amount as the EMF. And as you'll see in our next example, regardless of the strength of the resistor. It just happens to be in this example that each one is taking 10 ohms, but it doesn't matter. This could be 10 ohms, this could be 1,000,000 ohms, this could be 1,000,000,000 ohms, and each one is going to receive 9 volts of potential difference. So what's going to be different? Well, it's going to be the current. So let's calculate the total current that is going to go through the circuit first. So the entire circuit is going to receive total volts is 9, and the total resistance, we haven't calculated the resistance yet. So this is a parallel circuit, so we have to look at the reciprocal of each individual resistance. So 1 over R1 plus 1 over R2 plus 1 over R3, and this is 1 over 10 plus 1 over 10 plus 1 over 10. Remember that this is 1 over RT. So you actually have to take the inverse of what you get here before you can calculate the RT. So the RT here is equal to 3.33 ohms. It's kind of neat. If you look at this, each resistor has 10 ohms, but when you put them together, you actually have a total resistance that is less than the lowest resistor that you put into the circuit. So by putting these resistors together in parallel, you actually reduce the resistance. You make them fight back harder. So that gives you more voltage because each one is getting 9 volts. Compare this to our example 1. Okay, so now that we've calculated the RT, total resistance, which is 3.33 ohms, the total current in this example is 2.7 amps. So that is the total current that is going through the entire circuit. So now we need to know how much current is going through each one. So I1, we need to now apply Ohm's law for this one. Again, we look at Kirchhoff's rules before we can consider Ohm's law. So now that this is analyzed in terms of loop and junction, we can calculate the individual current. So I1 equals V1 over R1. And the total volts is the same as the individual volts. 9 volts divided by R1 is 10 ohms. So the current is going to be 0.9 amps. Now, because they each have 10 ohms of resistance, they are going to be exactly the same. So I2 is also 0.9 amps and I3 is also 0.9 amps. And if you take a look at the sum of all three, you should get the total current. And you do. And that tells you that we did our calculation correctly. So just to summarize this one example here, this is a parallel circuit with the same amount of resistors, but it doesn't matter because the voltage is going to be the same individually as that of the total voltage. So 9 volts total voltage for the entire circuit, each one is going to receive 9 volts as well. Because in a parallel circuit, what is the same as the total? And the individual ones are the voltage. So we apply the reciprocal here for finding the total or the equivalent resistance. And we have less than the individual resistance because that's what happens in a parallel circuit. The total current is 2.7 amps for the entire circuit. And if you look at this, because each one is the same, another way, because they have the same R, you could just take the total IT and divide that by 3. And that gives you the 2.7 divided by 3, which is 0.9 amps. So this is another way of calculating the individual current because you know that they have the same resistors. If they have different resistors, what do we do? Well, then we'll have to calculate each individual ones using Ohm's law. So let's actually do one more example here. Let's do example 4 in our circuit analysis. So example 4, this time we're going to have, again, a parallel circuit, exactly the same configuration as our example 3. See, these, I call them monster fangs. If you look at it, they do look like vampire fangs, don't they? They look like monster fangs because when I call it monster fang, it reminds me what the resistors do. Well, they do fight those flow, right? They resist, they chew up those electrons and they spit it right back into the system. So energy is conserved. Let's again give this circuit 9 volts. This time, this is going to be different. So R1 is 10 ohms, R2 is now 20 ohms, and R3 is now 30 ohms. So what do we have that is the same in a parallel circuit? What is the same as the individual ones and the total? The same voltage. So we know again that the VT is equal to V1 equals V2 equals V3, regardless of the strength of the resistance. So each one is going to be 9 volts each. Okay, we didn't even need to use Ohm's law for this one. Again, this is another proof that we need to look at Kirchhoff before Ohm. So I always look at analyzing what kind of circuit do we have here. Once I've identified that this is a parallel circuit, I just have to remember the junction rule. You have junctions here. So you have the current is going to go through R1 and it will go through R2 and R3 in different paths. Because you have more than one path to follow, the voltage is going to be unaffected. Because you're going to kick R1, but you don't have, you go back, this 9 volts is going to come out of this positive terminal. Okay, it's going to feed 9 volts to this R1 and it's going to return with 0 volts of potential when it goes back to the terminal, the negative terminal. So same thing here, 9 volts going to be used up by R2. By the time it goes back, 0 volts. The same thing with R3. 9 volts is going to be dropped off here in R3 and go back with 0 volts. So each of these resistance is going to receive 9 volts, the same as a total. That makes sense. So once you know that this is according to Kirchhoff, you don't even need to use Ohm in this case. No calculations required for voltage because the individual voltages are the same as the total volts. So that is 9 volts each. Okay, so now that we know that, we need to analyze the current. So current is going to be different. But before we do that, let's calculate the total resistance. So 1 over R1 plus 1 over R2 plus 1 over R3. I'm going to do this in detail for the reciprocal. So 1 over 10 plus 1 over 20 plus 1 over 30. Now remember, this is 1 over RT, not RT. Now in your calculator, you have different ways to do this. You can, the calculator that I got here, you have this x to the power of -1. So use those buttons instead of typing in all these numbers. So look for this button in your calculator, that's x to the -1, or you have 1 over x, you use that. So all you need to do is type in the number 10, press one of these buttons, plus 20, press one of these buttons, plus 30, then one of these buttons, press the equal sign, and then again, one more time, one of these buttons. Okay? That will give you the reciprocal. So I just took, actually, I'm going to show you here. So I'll just press number 10 and then these buttons. So I'm going to use that plus 20 and then this button again plus 30 and then that button. Okay. Press the equal sign and whatever number you have here, actually I'm going to do it right here. So 10, I just do second function for mine. Know how your calculator works because every calculator works differently. You see here I have 0.183 repeating. I have to press that button one more time because remember this is 1 over RT. So for me to actually calculate RT, I need to press that inverse button one more time. So this is 5.45 ohms. That is the total resistance of this circuit. Now that we know the total resistance, we can calculate the current. So IT equals VT over RT. Total volts is 9 divided by 5.45. Again, because this is a parallel circuit, it gives you the total resistance. It's still lower than the lowest resistance that you have in the circuit. This is going to give you 9 divided by 5.45 is equal to 1.65 amps of total current running through the entire system. Now, this is going to be different current because it's a parallel circuit. So now we can calculate the individual ones. So Ohm's law to the rescue. This is when you need Ohm's law equation. Once you've analyzed the circuit in terms of Kirchhoff. Again, Kirchhoff before Ohm. So I1 equals V1 over R1. V is 9 volts divided by R is 10 ohms. So this is 0.9 amps. And I2 is equal to V2 over R2. So 9 volts divided by 20 ohms. And this is going to give you 0.45 amps. And last but not least is I3, V3 over R3, 9 volts divided by, this is the one with the highest resistance. And guess what's going to happen to the current? It gets the least amount of current. Why? Why is there least amount of current that is going through this one? Well, because it has the highest resistance. The more you resist that current, okay, the harder it's going to have a hard time going through it because it's fighting back. So that is our circuit analysis.